tetrahedra which are joined together, and you replace every once in a while. So, you will get something like this. So, when there are only silicate tetrahedra, there is no charge essentially, but the moment you have this, you saw that it is Al O4 5-. So, this has to be balanced by a positive charge. So, you have a metal along with this. So, this now can form cages. So, you could have cages like this, where you might have already encountered this in some form. And you fill this up. You must have seen this. So, you have similar kind of network, except that every once in a while you replace this with alumina. So, these are zeolites, and these can have structures with cages in it. So, you can imagine this situation, except that you put a lot more of these silicates, replace every few of them with alumina, and you will get cages like this. And as you can imagine, there are positive charges on this. So, the silica alumina network that you have got has Lewis acid sites, and this Lewis acid sites arise as a result of the aluminum which is outside this framework. So, these are your zeolite structures, and they form cages into which you can trap, these cages trap reactants. And you have, if this positive charge is an H plus, then it happens to be a Bronsted acid site. Whereas, if you have extra framework alumina, then you have Lewis acid sites. So, these zeolites happen to have cages which can trap reactants as well as Bronsted and Lewis acid sites. So, these are very good catalysts for many of the steam reforming reactions that is used in the petroleum industry for getting cracking of petroleum, and they work through these cage formation which traps species. So, this is a large class of catalysts which are called zeolites, and the thing to understand is that they are formed by a network of silicate and aluminate tetrahedra joined together to form cages in which reactants are trapped, and there are both Bronsted acid sites as well as Lewis acid sites which allow the catalytic power of the zeolites to come into place. So, that is one class of catalysis that we needed to look at. The other thing that we need to look at is enzyme catalysis. Now, enzymes are polymers, and you might have encountered this in your study of organic chemistry. These are polymers with amino acids as the monomers. What are amino acids? If you have a molecule with this general formula, this is an amino acid, this is an amine, and this is a carboxylic acid. So, this is a particular class of amino acids that we are looking at, and there are these R's can be 20 in nature. So, there are 20 different R's, and you take one amino acid like this, you put it beside another amino acid where I have a different R, call it R prime, and now I lose a water molecule from here, and if I lose a water molecule from here, I have what is called a dipeptide, which looks like this. And there is no reason for you to stop here. You can add other amino acids and you build a long chain like this. So, this is a dipeptide, and if you did this infinitely, you will get what is called a protein, and enzymes are proteins. And what happens is, because of restricted rotation about these enzymes have very interesting shapes. So, you could have enzymes which look like this. So, this is made up of these polypeptide chains which curl up to give you some very interesting shapes, and this is what might be called an active site of the enzyme. Okay. Now, these enzymes are very, very efficient catalysts. They are present in our body and they catalyze a whole set of reactions, and here is how they are classified. So, the enzymes are classified based on their action, and I am listing here some that there are 6 different classes. If I have a reaction which goes AH2 plus B, where I have a transfer here, then this is called an oxidoreductase, and here is an example of an enzyme which does this kind of reaction. In this case, I have the X group which is transferred from A, it is attached to A in the reactant side and it gets transferred to B. So, if X happens to be an amino group, then it is called an aminotransferase. The third kind, which is very popular, is if I have a molecule AB and I want to cleave this bond with the presence of water, I can get AH plus BOH. So, this is an example of a protease, and so on. And there are 6 different classes that is typically observed of the kinds of reactions that these enzymes do, and here are the various examples for each of these categories. But the important thing for us to realize is that whatever enzyme you have, these are all made up of these amino acids which are put together one after the other. And a simple way of thinking about it is, think of each of your R's. So, think of each of these amino acids let me just think of this amino acid as a bead. Okay, call this a red colored bead, and if I have a different R prime, let me call it R prime, let me call it a square bead. Now, I put these two together, I join them and I get something, and I keep going like that. And I can put various things together. So, think of this as a necklace, and I have this long chain, and you know, when you have a long chain, long necklace with different size beads, different colored beads, when you put it, it does not take the shape of a linear thing, it does not sit like this. What it does is it folds up, and when it folds up, it takes a very strange shape. And based on what you have here, so it could be blue, red, black, blue, blue. But if I have a different order, then the shape it takes is different. So, based on what I have here, what are the beads which I have put together, the shape that the enzyme takes is finally very different. So, I could have something which, so imagine that I have an enzyme which folds up in such a way that I have something like this. And if I have a molecule that has this shape to it, so imagine that I have a molecule like this reacting with a molecule like this, what happens is these two molecules will come and bind to the enzyme. When they bind, what happens initially is that the binding is not very good. But the moment there is some amount of binding, the molecule, the enzyme will twist in such a way that it will enhance the binding between these two. And so, you will get, now let us see if I can draw the same shape again. So, now it is bound. And once it is bound, I have a reaction between these two species. So, this enzyme, the blue enzyme which has this strange shape, gives the opportunity for these two things to bind. So, the way this reaction works is that called this, so in the terminology of enzyme kinetics, this enzyme is represented by E. And these two things are called the substrates, called this S1 and S2. So, what happens is initially the enzyme binds the substrate. So, I will get an E plus S will bind and I get an enzyme substrate complex. I have a reaction of this enzyme substrate complex to give you a product, call it the enzyme product complex, and then this goes away and you will regenerate the enzyme and give back the product, and this cycle repeats itself. So, I have the enzyme and I have the substrate to give you an enzyme substrate complex, undergoes a reaction in the presence of the enzyme with the substrate bound to the enzyme, gives you an enzyme product complex which then falls apart to give you the enzyme and the product itself. And if you drew the Gibbs energy, the energy versus the reaction coordinate profile, it is identical to what we had in the case of the catalyst. So, let us imagine that I have this reactants, I have products. What we are saying is there is an enzyme substrate complex, the enzyme product, and this. So, this is the uncatalyzed reaction. This corresponds to the enzyme substrate complex. This corresponds to the enzyme product complex, and this gives you back the product. So, this reduced energy barrier, so this activation energy that you have got for the reaction on the enzyme is much lower than this, and this leads to extreme efficiency for the enzyme catalyst reactions. And the efficiency of enzyme catalyzed reactions is characterized by a quantity which is called the turnover number, and I have listed some of the turnover numbers here. Carbonic anhydrase is by far the most efficient enzyme that you can think of. This enzyme catalyzes the reaction of carbon dioxide with water to give you bicarbonate. And what this tells you is that per second 600,000 molecules of carbon dioxide and water combine to give you bicarbonate. This is more efficient than any catalyst that a human can synthesize so far. This is very, very efficient, and I have listed here, no reason again to remember all of these. All that I am trying to do is to give you an idea that some of these turnover numbers, which is a measure of how many molecules per second a reactant gets turned over into a product, and more the number, higher is the efficiency. And you can see that as you go down here, you have various enzymes. This is by far one of the most efficient enzyme, and as you go down, the number keeps on decreasing. So enzymes are extremely efficient. Our whole natural system, our body for example, completely works with enzyme catalyzed reactions. Right? Penicillinase, for example, is the enzyme that breaks down a penicillin antibiotic which is given to the body. So this breaks down the penicillin antibiotic. Lactate dehydrogenase is what acts when you drink milk, for example. So all of these enzymes are things that are present in the body, and they have various levels of activity. There is, of late, there is also use of enzyme for industrial production of compounds, and there are advantages and disadvantages for enzyme catalyzed reactions, and they are listed here. They have very high enantioselectivity, and you can imagine this because you have these enzymes and they have these strange shapes, and obviously even if there is a small change in the reactant that binds, the enzyme will be unable to bind that thing, and if there is no binding, then there is no reaction. So they have very high enantioselectivity, they have very high regioselectivity, which means that if you have a reaction at one site, it won't react if there is a change in that. And you can have reactions happen at very mild conditions. This is of great importance because you don't want to subject your reactants to harsh conditions, and since the enzymes contain proteins which are amino acids and they are available in nature, they don't work under harsh conditions. So most enzyme catalyzed reactions happen under very, very mild conditions. So the other big advantage which is becoming increasingly important in recent days is that the enzyme catalyzed reactions happen in a water medium. This is very important because nowadays we are interested in what is called green chemistry, because you want to minimize the amount of bad things that you put into the environment. So any reaction that happens in a water medium is preferred over something that happens in an organic medium. So this is of great importance. So people are trying to design catalysts which will work under conditions of when in water medium. So and all enzyme reactions, because they are natural polymers, exist only in water medium. So this is naturally enzyme reactions happen in water medium. There are disadvantages to it in that it has very low specific activity, and because these enzymes are proteins which contain natural amino acids, the moment you raise the temperature, these proteins denature. And you have seen this protein denaturation. If you take an egg, the eggshell, after you boil it, has undergone a change. What was solid initially, but when you boil the egg, it undergoes, it becomes, the shell becomes hard, and there is a denaturation process. And that is an example of a protein, or in this case a protein, and since all proteins are enzymes, they undergo denaturation, which means that the active configuration of the protein is changed. Similarly, the amino acids contain groups which have either basic or acidic side groups, and they have a specific range of pH over which they act. So, this limited temperature and pH range of activity, when you go into industrial setting, becomes a disadvantage, although normally it is an advantage. The other thing that you have to notice is that enzymes only catalyze a limited set of reactions. You can't imagine every conceivable organic reaction have an enzyme catalyzed equivalent. People are working towards it, but as things stand, there are very limited set of reactions that you can use for enzyme catalyzed studies. And from an industry standpoint, the biggest problem is that if you try and develop an enzyme to do a particular reaction, before it becomes marketable, it takes a long development time and extreme expenditure. So, this is one of the reasons why the use of enzymes has lagged behind in industry. But as the push for green chemistry, that is reactions in a water medium, takes precedence, you are going to see more and more reactions which are enzyme catalyzed. And the enzyme catalyzed reaction, as we have seen, is very straightforward, and it is an adaptation of what we saw in heterogeneous catalysts. I will just recap this before I close for the day, and that will close the subject of catalysis. So, this is how it goes. You have an enzyme, it grabs a substrate to form an enzyme substrate complex. This enzyme substrate complex will undergo a reaction to give you the product, which is still bound, and the enzyme product complex then falls apart to give you, regenerate the enzyme, sorry, this is not right, and the product. And this is how it works. This is attributed to two scientists. This mechanism is called Michaelis and Menton. And if you looked at the rate of the reaction of these enzyme catalyzed reactions as a function of the substrate concentration, you will find something which goes like this. So, typically in all enzyme catalyzed reactions, you will see the rate variation with substrate go like this. So, with this I think I will close for the day. What we have looked at today is how a heterogeneously catalyzed reaction works. We discussed the Langmuir-Hinshelwood mechanism, where you have contact catalysis, where you have two reactants which come and bind to a surface, and then I have a reaction on the surface, which means that although the activation energy is low, the number of collisions are also low, but they are somehow offset each other. And typically we also said that the extent of binding has to be optimal for having the largest rate constant. Either if it is too low or if it is too high, then the rate constants are suboptimal, and that is because of adsorption phenomena. And then we looked at briefly zeolite and enzyme catalysis. With this we will close for the day. In the next session we will look at colloids, which will close this discussion on surface chemistry. Thank you.